Welcome back. And here we go. We are going to do hydrolysis of carboxylic acid derivatives. And we're going to note that the top two most reactive derivatives are the acid halide and the anhydride. They do not require a catalyst for this hydrolysis reaction. They will go simply upon mixing the derivative with water. So we say they are very reactive if you react them with water and no catalyst is needed. Down here, esters are more robust. To do a hydrolysis of an ester, you need either a strong acid such as sulfuric acid or toluene sulfonic acid. And you can do it under basic conditions. We will treat that in a separate section called saponification. And amides, same story. They're even less reactive than esters. So not only do we need a strong acid catalyst, but we need a very, very large excess of that acid catalyst to push equilibrium away from an unfavorable situation towards the hydrolysis products. Similarly with nitriles. In fact, the hydrolysis of a nitrile creates first an amide, and then the amide undergoes the hydrolysis that we're going to see with the amide hydrolysis. Let's look at the first two because they look identical so far to me. Water is the attacker in both of these. Creates this tetrahedral intermediate. Why is it called such a thing? Well, it started as an sp2 atom and it ends as an sp2 atom. So in the middle, we have a carbon that's sp3, which is tetrahedral. It's a key intermediate. If you're looking carefully, black arrows being first, there would be a second tetrahedral intermediate caused by the neutralization of the oxonium ion. And I've drawn that one down here. That's another sample tetrahedral intermediate. That would be breaking it down into the steps. We know we're breaking it down into steps by stating it here and here, but here's what you would have in the middle. And then elimination of the excellent leaving group, which is not hard to do, will cause creation of a carboxylic acid. And there's your excellent leaving group. This mechanism looks the same. The only difference is it'll be a little slower because your leaving group's not quite as good. Water attacks, you get a tetrahedral intermediate, which neutralizes and eliminates. The elimination would be a little slower than with a chloride. And there's a little acid-base chemistry going on at the end where the carboxylate is a more basic than a chloride. It will neutralize hydronium. Chloride will not neutralize a sufficient amount of hydronium here to even worry about. This is a side reaction. I wouldn't even make you do that reaction for me. Getting to here is the important thing. So what's the only difference going to the next one? Well, one, you've got a lousy leaving group, and two, you still got a poor nucleophile. These nucleophiles didn't care because these have excellent leaving groups attached. This one has a poor leaving group. It's not going to react unless you activate the carbonyl. Please tell me you know that's not the first time we've mentioned activation of the carbonyl. So we're activating the carbonyl, and then we're attacking it with the poor nucleophile, and then it looks kind of like what we did in the top two, except now we have an OH up here. To do your elimination, you're going to have to deprotonate that and then protonate the OET as it leaves. You could have broken this down into a third step, right? I will accept this. I would say after you've done this neutralization of the oxonium, a second step would be to protonate this O to make it a better leaving group. And then the third step would be this gray arrow, and another gray arrow that ends on the O. But if you like this mechanism, stick with this one. We have exactly the same story down here. I'm sure you can handle these on the test. There's no difference here, just changing around the conjugate bases. And neutralizing the oxonium has been the same every time. And where is the big difference here? When you created the leaving group here, it was an amine, which is itself a base. A base will consume your acid catalyst. So that makes your acid catalyst not only a catalyst, but a reagent. So if you use a very small amount of sulfuric acid, yeah, you're going to do a hydrolysis of maybe 1/100th of 1% of these, and then your catalyst is shot because right after the catalyst did its thing, you use the catalyst here, you made the catalyst here. It's going to react here before it does any more of this. So it's being consumed. So that's why we have a huge excess of sulfuric acid, to make sure we push this to the end and have enough leftover sulfuric acid to maintain the catalytic cycle going on here. Now with the nitrile, I put it way over here because the amide right here that we started with for this section is an intermediate in this section. So we don't have an oxygen to activate here. The next best thing is the nitrogen. It has a lone pair. It can be activated by protonating it. Then water does an attack to create an oxonium. And then if you look carefully at this, this is a tautomer of an amide. All you have to do is move the position of this H and this pi, and you have this molecule. Isn't that the definition of tautomerization? Moving a H and a pi. So this is a tautomerization step. We've seen many of those. It's acid catalyzed. Here's sulfuric acid. And then you have your amide after that. And there's the hydrolysis of the amide. So you're not using any more sulfuric acid than before because it was a catalyst being used from here to here. We regenerated our catalyst. And then we did it as a catalyst for the tautomerization. So we haven't used up sulfuric acid even to get to here. And then we didn't use it up to get to here, but this step uses it up at the end. So you still need a large excess of sulfuric acid. Take home message: hydrolysis of any carboxylic acid derivative gives carboxylic acids. And we need to know these mechanisms, all of them. But I'm pretty sure you guys can handle those. They're not too bad. This one is a dead ringer for the Fischer esterification right here. In the Fischer esterification, you replace water with an alcohol, and you do all the same arrows. And we combined a couple steps in there. And what would happen if we did what I just said, replace water with an alcohol? It doesn't really change a thing. This is the same mechanisms as on the previous page. You don't need a catalyst for the first two because they have excellent leaving groups. Starting with this ester, you do need a catalyst. The reason why the amides didn't show up in this page is the reaction doesn't work very well. So we're not even going to cover it. I call these reactions alcoholysis because you're using an alcohol to break apart the derivative. And you're always ending up with what functional group here? What functional group do we have? Every time. It's an ester. Esters. So what do we call this last one where we started with an ester and ended with a different ester? That would be a good word to use right there, wouldn't it? Trans-esterification, going from one ester towards another. And why would you ever want to do such a thing? It seems pointless. I already have an ester. Why do I have to make it into a different ester? Here's a simple scenario in which you might want to use this protocol. Say there's a very cheap version of an ester found in nature. Like it's maybe pennies to the gram, but that has no medicinal value. If you change the R group in the ester, maybe all of a sudden it's a good antiretroviral treatment or something. And that would be a good drug. You would just do a trans-esterification to make the one ester into a different ester. And I want to say it again, this is the same mechanism as the Fischer esterification. The only difference is this will be an OH and a carboxylic acid for the Fischer esterification, and it will leave as water instead of leaving as HOET. It'll be HOH, but the mechanism is identical. Protonation followed by attack. Tetrahedral intermediate gets neutralized and then eliminated. Fischer esterification mechanism. And I believe there's a typo right here. That H is a Chem242 vestige. It shows up when I move things around and I don't move a plus sign. Anyway, you don't need to know the explanation. It's lame. There's an extra H in here. I can't erase it. I'm trying. It's HOI boo like it was in the beginning. HOI boo. Typo. Can't see it. Okay. So alcoholysis of carboxylic acid derivatives creates not carboxylic acids, but carboxylic esters. And then we'll use aminolysis. That's not using an alcohol, it's using an amine. And you'll notice the same scenario as the beginning. We don't need a catalyst here or here, but for some strange reason, we don't need a catalyst down here for the ester either. Our previous two examples of hydrolysis and alcoholysis both required an acid catalyst. Why is that no longer necessary for our ester here? This is a great question. Maybe I'll put it on the test. Well, let's see. The reason we needed a catalyst with the esters was this is not very reactive, and this is also not very reactive. Bad nucleophile, not a very reactive electrophile because it has a lousy leaving group. I don't think the lousy leaving group changed. It's the same leaving group here, isn't it? It's an OR group. That's a lousy leaving group. But we have a better nucleophile. Oh, amines and ammonia, which is basically like a naked amine. It doesn't have any carbons on it up here. Amines and ammonia are moderate nucleophiles. That's a lot better than being poor. So no catalyst needed here. Yeah. And what do you make every time you do any of these reactions? And attached to carbonyl, and attached to carbonyl, and attached. These are all amides, aren't they? With ammonia, you're going to get a primary amide. With a primary amine, you're going to get a secondary amide. Hey, the number's going up by 1, isn't it? And with a secondary amine, you get a tertiary amide. Why? Well, you're adding the new carbon that's the carbonyl, aren't you? What's the word for adding the carbonyl group again? Go back to the beginning of the lecture. You're adding this to the nitrogen. It's an acylation. That'd be another name for this type of reaction, right? Nitration. Nitrogen. Once again, writing and talking don't always mix. We're putting an acyl group on nitrogen. We called it aminolysis because the nitrogen was being used to break apart this derivative. So this is a great way to make amides. We have learned lots of ways of making these new functional groups. And then we'll talk about the base-promoted hydrolysis of carboxylic esters. What does this mean? Base-promoted hydrolysis. It's not a catalyst. The base gets used, gets consumed, and the name of the process, if it's done with natural esters of fatty acids like these, here's a triglyceride. The name of the reaction is saponification. It's from a Greek word sapos, which was an island where there's lots of rumors in history that this was the first place that soap was created, on that island. I haven't got a good definitive version of that story to tell you, so I won't. But anyway, we're taking a ester of a fatty acid. This is not one found in nature, but it would create a soap nonetheless. And you're reacting it with aqueous sodium hydroxide. So you have a really good nucleophile here. That's why we don't need a catalyst with our ester. This is even a better nucleophile than an amine. And we didn't need a catalyst with our amine, did we? So hydroxide attacks, you get an O-. And then you get this thing to come back, and this leaves. We could combine those two steps. I'll do it right here. OET and hydroxide in green. And we'll go red first. And our traditional colored version of blue second. And the attack is first. Don't need a catalyst because it's a great nucleophile. You need the lone pair that's already here to come back. And kick off your leaving group. And that will get you right to this step right here. So saves you from drawing the tetrahedral intermediate. But you know there's a tetrahedral intermediate because the red arrows would cause a carbon with 4 sigma bonds. And then you can't stop this last step. Your leaving group was a strong base, OET minus, and you've just created a carboxylic acid. They cannot coexist. They must react with each other. pKa says so. We're going from pKa 5 to pKa 16. Remember, ethanol is 16, not 17. And yeah, you can't stop that. And if the R group is substantially large, and when I say substantially, I mean 11 carbons or more, you have a good soap molecule. Reason why there's soaps will be discussed on the bottom of the screen. I stole this one from the last chapter. You'll notice it ended up in the starboard notes, but we never talked about it. Well, I found it was better to talk about it here. Here, I'm taking a natural triester of glycerol. Here is glycerol. It is the product after hydrolysis using base, also known as saponification. And every one of these esters reacted by this mechanism. So 3 times, and we generated 3 soap molecules. We got oleate and myristate and linolenate. You don't have to know those names. In terms of fatty acids, I always like to remind my students that the ones with the more double bonds are generally more healthful for you. They'll have more benefits to your health. And the ones that are saturated are less healthful. They tend to accumulate and do things like block your arteries and veins. So this reaction creates 3 nice soap molecules. It also creates glycerol, also known as glycerin, which is useful to keep in the soap as well, because you've noticed that some soaps dry your hands out, right? Well, if there's glycerol in there, that keeps moisture in. It's called a humectant. Humectant. It's got humidity as its prefix, doesn't it? And those are things that let moisture or keep moisture in. So how does a soap or a detergent work? Well, what I've done is I've taken my stearate ion, which I would have made up here, stearate ion. I drew out all the carbons. This took forever to draw, by the way. And there's the stearic acid. If its base is a good soap. And why is it a good soap? Because these ions out here, they love water. What's the word for that? Hydrophilic. And hydrophobic parts, they avoid water and want to stay together because they don't, water's not attracted to them and they are attracted to each other. So what will happen is all of the molecules will form a sphere. This looks like a circle because we're talking about a page, but really it's a three-dimensional sphere. And it would be a ball, right? And outside is the water. And inside are the parts avoiding water. And if you have clothes that have grease on them or your hands have grease on them and you wash them, the sphere will trap the grease in the middle because that part doesn't like water either. So you've given it a better place to be. It's got better intermolecular forces with these tails out here. So you have trapped that grease molecule in this thing that can be washed away. This sphere gets washed away. And it's water soluble. Why? Because all these ions on the outside. So that's how you clean stuff. Use soap. Now, the only difference between a soap and a detergent is the carboxylate on the outside here for a soap comes from natural sources. In detergents, those carboxylates are changed to sulfonates or phosphates or even ammonium ions, charged things, but they're all synthetic. And even though we did this work in the lab, we say because it came from a natural molecule, a triglyceride found in nature, that it's a natural thing. So we're going to call it a soap, even though we did some chemistry on it. And if we derive these into different groups, like sulfates or ammonium ions or phosphates, then they're called detergents. Okay. And that is going to close up this segment here. And we'll pick it up with the rest of the chapter when we come back. See you very soon.